Okay. Hello student, good afternoon and welcome to the live session of the course on optimization methods for civil engineering. So we already received a few questions and I will try to clarify those questions initially, then I will take some live question if you have any other questions. So let me present those questions. Okay, then the first question is related to Newton's method. So this question is that how this method can be applied for solving this problem. You can see, so this problem was asked in question number 8 of assignment 4. Minimize, this is a function of x1 and x2, and the function is x1 plus x1 minus x2 plus twice x1 square plus twice x1 x2 plus x2 square. So this is a quadratic function, and here the initial solution is given. That means you have to start your iteration from this particular initial initial solution. Okay, so this is given, that is x1 equal to 0 0. So that is the starting point, and we have to apply Newton's method. So if you recall, the Newton's method can be, suppose we can write that xi plus 1, which is equal to xi minus, this is the Hessian matrix, inverse of Hessian matrix into del f basically. So if you look at, suppose we already discussed that, suppose x1 I can calculate. So this is your x naught plus alpha d. So in case of Newton's method, d is calculated this is inverse of Hessian matrix into del f at x naught basically. Okay, so here this x naught is given, so I'm writing here xi, so it is basically x naught, and this is 0 0. And then if I calculate the Hessian matrix, okay, so this is 4 2 2 2. So how you will get the Hessian matrix? So I can get the Hessian matrix something like this. So this is del square f by del x1 square, then this is del f by del x1 del x2, and this is del square f del x2 del x1, and this one del square f by del x2 square. Okay, so now if I take second derivative, so finally I will get this Hessian matrix, and Hessian matrix is 4 2 2 2. Okay, and then if I calculate del f, so del f I am getting here, so del f is your 1 minus 1. So this is your del f, so 1 minus 1. So I have calculated del f. This is the first derivative at x naught basically. So x naught means that is 0 0. So I'm getting 1 minus 1. Now if I put this in this particular equation, that xi plus 1, so this 0 0, so this is your x naught, and this is the Hessian matrix, inverse of Hessian matrix into your del f at x naught. Now if I calculate the inverse, so inverse is, this is half, this is minus half, this is minus half, and this is 1, and I'm getting 1 1, and finally if I simplify it, so I'll be getting 1 by this is your minus 1, and this is 3 by 2. Okay, and this is a quadratic function, so therefore a single iteration of Newton's method will give you the solution, and solution you should get -1 and 3 by 2. method. So what I'm doing, we are calculating the direction using this equation, that is inverse of Hessian matrix into del f at x naught. And in case of steepest descent method, so we are going negative of the gradient. Okay, so negative of the gradient. So if you do that, so finally I will get the solution, and because this function is a quadratic function, so therefore I am getting the solution in single iteration. I hope this is clear. So let us go to the next question. So in case of genetic algorithm, suppose your problem is a minimization type problem. Suppose I would like to minimize fx, okay, and then I can convert this problem to a maximization problem, so by 1 plus f. So now question was, in this case particular question is, why not it is 1 by f basically. So if you're putting 1 by f, so it is a minimization type problem. Suppose f may be 0 also. Okay, so in that case you will get this is 1 by 0. So therefore, in order to avoid that one, so I am using 1 plus f basically, and basically if it is going negative, so you can also take absolute value. So what will happen now if f equal to 0? So that means, suppose if I write like this, so this is minimization of fx, and which is your maximization of capital Fx, okay, and which is equal to 1 by 1 plus f, okay. So basically, so now here what will happen, that if f equal to 0, so in that case capital F will be equal to this is capital F will be equal to 1. Okay, so maximum value is 1 you are getting. And if you are suppose if f is infinity, so in that case you will get you will get this will be, suppose f is a very large number, okay, infinity, so then capital F you are getting 1 by infinity. Okay, so therefore the maximum value you are getting here 1. So you can do that. Sometime depending upon what problem you are using, you can also take this, I can also take 10, or you can also take 100, but we are not using 1 by f. Okay, so in order to avoid this situation. I hope this is clear. So this is actually in this case, so we are writing 1 by 1 plus f. Now the third question is, so here how to select this x naught value, and then how to get this del f x naught. Okay, so this was a solved problem. So let me go to the problem. So I discussed in the class, so let me go to the problem, and I will explain how we are taking that x naught value and how we are getting the derivative value at x naught. Okay, so this is the problem I have solved. This is a function of x and y. So this is x squared plus y squared plus 4. And this x naught is basically user defined value. That means user has to give a point. Suppose let me take a single variable function, and this function is suppose this is your x, and in this side it is fx. Okay, so now this function is your fx function, and I would like to find out the maximum of this particular function. Now what I can do, I can start my search from here. So this is my x0, or my x0 may be somewhere here, or my x0 may be somewhere here. So therefore the user has to define a value of x0. So in this case I have defined that x0 is 1 and 1. So you can also try with x0 0 0. You can also try with x0 maybe 2 2, or you may start x0 value of 5 5. Okay, so depending upon what is the range of x and y, so you can start. So in this case I have just taken that this initial value is 1 1. Now next is, so I have used the steepest descent direction method. So this is the steepest descent direction method. So in case of steepest descent direction method, the direction is given by the negative of the gradient at that particular your point. So here I will start my algorithm from x0. Okay, so I will start my algorithm from x0. So therefore I have calculated the direction that d equal to minus del f x0. So then I'm getting 2 2. Okay, so I said that, so 2 2 means, so you are going 2 unit in x direction and 2 unit y direction. That means you are going along the 45-degree line. So you can also take, so I can also take 1 1, that same direction I will get. So this is the 45-degree line. So whether you are using 2 2 or 1 1 or any, or you can divide it by any, suppose I am dividing it by 2, so in that case I will get 1 and 1. So I have taken here, so negative of the gradient, so therefore this is minus 2 minus 2, and then if I put it, so this is my x0, then plus alpha, and this is minus del f x0. Okay, so you are getting this value, and if you are putting in equation 1, so this is the equation 1, so this is the equation 1, and so you are getting this equation, and this is in terms of alpha. And if you take the derivative, so you need to find out what is the value of alpha, and you are getting the value of alpha equal to 2. I hope this is clear how we have considered the value of x0. So x0 is user defined. That means you have to define what should be the value of x0, or you can say, now also we have discussed genetic algorithm. So now you can see the difference between genetic algorithm and classical method. So here what you have to do, you have to define the initial solution. That means the x0 you have to define, and this is user defined parameter. So you have to define this particular value. Okay, so and then you can calculate the direction using the negative of the gradient. I hope this is clear. So I am getting this final solution. So this is the hand calculation I have shown. Now let us go to question number 4. Okay, so this is related to quadratic approximation method, and the question is that what is happening at this particular time. Okay, so let me explain that one. So let me go to the slide. So here, this is the problem I would like to solve. So this is the problem I would like to solve, that is x1 square plus x2 minus 11 and whole square, then plus x1 plus x2 square minus 7 whole square, and this is the starting point. Starting point is 2 2. Again, I would like to state here that this is a user defined your starting point. That means I have defined here. So in your case, you have to define this starting point, and in exam this starting point will be given to you, that this is the starting point. But when you are solving your problem, okay, so in that case you have to define the starting point. Okay. So now this function is not a quadratic function. So what I'm doing here, I'm doing the quadratic approximation using Taylor series. So up to the second derivative. Okay, so this is the Taylor series expansion, and I'm writing the Taylor series here. And then this is x minus x naught, this is del f x naught, and this is half, this is x minus x naught, then Hessian matrix, then x minus x naught transpose. So if you're putting these things, so you are getting, so now this function is a quadratic function, okay, so this is a quadratic function you are getting. Now this function I can solve using any method. So I said that you apply Newton's method, you apply conjugate direction method, and you can find out the solution of this quadratic approximated function. So so here what I'm doing here, so I didn't show you the how we have solved this problem. So you can apply Newton's method. Okay, so but I have solved using MATLAB here. Now if I am solving this thing, so I am getting from initial solution was your 2 2. Okay, so initial solution was 2 2, and after first iteration I am getting this solution. Okay, so x equal to x1 equal to this, and x2, so x1 I am getting 7.9268, and x2 I am getting minus your 0.561, and then I'm getting this the gradient value. Now considering this as the initial solution, the second iteration I am getting this one. Okay, so I have not shown you how I got this particular solution, but in this case I have used MATLAB function to get the solution, but you cannot apply any method. So maybe quadratic, the Newton's method or conjugate direction method you can apply, because you will get in a single iteration of Newton's method will give you the solution. So after doing some iteration, so finally I am getting this solution, and here you just see these gradients are calculated at the original function, and this gradient is almost negligible. So therefore you can say that you got the solution, and you are getting, in this case you are getting this particular solution, and you can stop your iteration. Okay, so I hope this is clear. So I have solved using a MATLAB function. You can also take any you can either use Excel solver, or if you're using MATLAB, or if you're using R programming. So now I think you also know, or you can also apply the R software. Now let us go to the next question. So this is about needs count, okay, and modified fitness value. So what we are doing here, so modified fitness value, we are calculating the original fitness divided by needs count. Okay, so now in the assignment, the question was, if needs count is large, then the solution is a crowded solution, whether this is true or false. So needs count is more means this is a crowded solution. If it is an isolated solution, then needs count value will be equal to 1. Okay, so there is no solution near that particular solution, so therefore needs count value will be equal to 1. And if it is a crowded solution, then this value will be more than 1. So therefore this needs count is if needs count is large, so in that case solution is a crowded solution. I hope this is clear. So we are calculating needs count in order to find out whether that particular solution is a crowded solution or isolated solution. So in case of isolated solution, we don't want to reduce the fitness value, because I would like to preserve that particular solution, is not it? So because it's an isolated solution, but there are crowded solutions. There are so many solutions on a particular region. So I would like to avoid this solution. How I am avoiding? I am just dividing the fitness value of the original function divided by needs count. That will reduce the fitness value of those solutions, and selection operator will not select them basically, because you are reducing the fitness value. But if there is an isolated solution, that I would like to preserve it. So, okay, so therefore in needs count, if needs count is large, then the solution is a crowded solution. I hope this is clear to you. Let us go to the next question, question number 6. So question number 6, if the tournament size 2 then base solution will have 3 copies. Okay, so yes, this will have 3 copies. Base solution will have 2 copies. If you have tournament size of 2, that means, so I have given an example. Suppose I have my population size. Population size is 6. So then what I will do, I will take 2 solution and they will play the tournament. You will get 1 solution because 1 will win the tournament. Then you will take another 2, then you will get another winner. Then you will take another 2, you will get another winner. So basically you are getting 3 solution in 1 round. So now this is your round 1. Okay, so now round 2 again you have to play. So you will get another 3 in round 2. So therefore the best solution will win the tournament both the time. So they will have 2 copies. Now in this case, the tournament size is 3. That means out of 6 solution, I will select 3, and these 3 will go for tournament and 1 will win the tournament. So therefore you will get 1 solution. Second time, so this is your round 1. Second time you are getting 1 solution. That means you will get 2 solution in 1 round. Then in the round 2 also you will get 2 solution, and round 3 also you will get 2 solution. Is not it? So what will happen basically? So now, so you are playing 3 rounds in order to get 6 solution. So the best solution will win the tournament in all the rounds. Okay, so in first round also he will be the winner, second one also he will be the winner, and third round also he will be the winner. So therefore the best solution will have 3 copies. Okay, so this is your, I hope this is clear. So we will get 3 copies. Then the next question is related to golden section source method. So this is assignment 3 and question number 8. Okay, so the question is, when applying the golden section source method to a function fx to find the maximum, and the f of x1 is greater than f of x2. Okay, so this is the situation. Now this function is a maximization type function. Okay, and I would like to find out the maxima. Now you are taking x1 and you are taking x2. Okay, so you are taking x1 and x2. So in this case, what is happening, that f of x1 is greater than f of x2. So f of x1, so this is the f of x1 and this is f of x2. So now what is happening, then optima is not there in this particular region. So therefore after this particular iteration, so what search space you are getting, this is the search space you are getting, that is your x2 xu. Okay, so this is the solution. Okay, so I'm not sure actually if we have given this solution, so we'll correct it. So C is not the solution, so A is the solution of this particular problem. So you are getting x2 and xu. So this region you will get. So which of the following statement is correct? The new search region will be x2 and xu. So I hope this is clear. So here f of x1 is greater than f of x2, and in that case this particular region will be eliminated. So optima is not there in this particular region. So this is your xl. Between xl and x2, optima is not there. So your optima will be between x2 and xu. Okay, so therefore this is basically this is the correct solution of this particular problem. Now another question in assignment 3. Okay, so here consider a problem. So this is given. So I have taken, this is x1 and this is x2. So this is a minimization type function. So this is a minimization type function, and here what is happening, that f of x1 is greater than f of x2. Okay, so f of x1 is greater than, that means optima is not there in this particular region. You can eliminate this region, or you can delete this particular region after this iteration. So therefore The correct option is x1 xl x1, that means xl. So this is the correct option. Okay, so this is this region you will get, and this region will be eliminated. So you'll be getting xl and x1. So this region xl to x1. So this region you will get. So this is the correct solution. Now there is another question. So here this is related to genetic algorithm. So this was a CAN design problem. So I would like to minimize the cost. Okay, so minimize the cost of this CAN. So here that you can calculate the material. So what material you required, and to convert that material quantity to cost, this C was used. So if you multiply by C, so C is 0.0654. So this is the value of C, and this is basically for this particular problem. So it's not that I'm assuming something. So if you multiply this, then you will get the cost of this particular CAN. So this is as per definition of the problem itself. Then in the problem itself, it has been defined, and C value here is 0.0654, and then this will actually convert the quantity of material to cost. So in this particular problem, C value was 0.0654. I hope this is clear. Then question number 10. So this is related to multiple function or multi-objective optimization problem. So this is multi-objective optimization problem. So far, whatever we have discussed, so we have either minimization problem or maximization problem of fx. Okay, and subject to your zjx is less than equal to 0 or hkx is equal to 0. So this problem we have solved basically. Okay, but this question is related to multi-objective optimization problem. So sometime what you may have, suppose I would like to maximize f1x, okay, and same time I would like to maximize f2x, and this is subject to your zjx is less than equal to 0 and hkx less than equal to 0. So this is a multi-objective optimization problem. Okay, so I have not discussed this particular your problem, but I will discuss this maybe your next week, or we have multi-objective optimization problem. So there I will discuss this particular problem. So how you can handle or how you can solve a multi-objective optimization problem, and what is multi-objective optimization problem, and how you can solve this problem using classical method as well as genetic algorithm. So that will be discussed, but as of now I have not discussed this particular problem. So that is there in your I think next week or next week. So you will have this particular topic. Then question number 11. Yeah, so the question is which of the following function has higher region elimination capability? So it is genetic algorithm. So there are some problem in the portal. So this is not interval halving method, but this is genetic algorithm. So this is you can actually eliminate more surface your area if you are applying. Sorry. This is not it's not genetic algorithm, it's a golden section search method. Yeah, so it's not interval halving, so it's golden section search method. Okay, So you can eliminate more area out of these: interval halving, then golden section search method, bisection method. So you can apply, it means golden section is the most efficient method, and you can eliminate the highest region if you are applying golden section search method, not the interval halving method, not the bisection method. Okay, so the area eliminated per function evaluation is more in case of golden section search method. Okay, so the key has been updated, so you can see. So this solution is B. Okay, so golden section search method is the correct solution. Yeah, this is related to whether your function is a positive definite or negative definite. So here, what we are doing, so you basically calculate the Hessian matrix. Okay, so you are getting your Hessian matrix, and then you need to check whether this particular Hessian matrix is a positive definite matrix or a negative definite matrix, or neither positive nor negative. Now question is that it's not the determinant value of this particular Hessian matrix. So what you have to do, how to check whether this Hessian matrix is a positive definite or not, basically. So you calculate the eigenvalues. Okay, so alpha I. So eigenvalues are negative here, so therefore this is a negative definite matrix. So, or you can do one thing, if your suppose you can calculate H1, so H1 is the first element. Okay, so this is A11, and H2 is basically the A11, A12, A21, 21, and A22. Okay, so now if H1 is, so you have to follow this particular rule, -1 to the power j. That means the first one should be negative, then second one should be positive. So if this rule is if it is followed, then you can say that your matrix is a positive definite matrix. But in this particular problem, the eigenvalues are negative, so therefore this is a negative definite matrix. So I hope this is clear. It's not basically whether the determinant of the Hessian matrix is positive or negative. So you have to check at the eigenvalues. So I hope I covered all the questions whatever we have received in the portal. So now if you have any other questions, so let me check that one. Yeah, so there is a question from one student. So this is about the niche count. Yes. Okay. So what we do basically in case of niche count. So suppose, I think I also explained this thing in my lecture. Suppose you have multiple optimal solution. Okay, so multiple optimal solution, and if you are applying, so I have also shown here, suppose if I apply GA here, so this is X and this is your Fx. So now what will happen if I apply GA? So this is the global solution, global maxima. Okay, so you will get this particular solution, the global maxima. And now if you are applying the niche count, so if I apply the modified fitness, so modified fitness is the actual fitness divided by niche count. So in that case, what will happen if there is a, because all the solutions are near the global optimal solution, so therefore what I will do, I will reduce the fitness of this particular your solution. I mean, suppose your solution, so what is there near the global optimal solution. Now I will divide it by niche count, because this is a crowded solution, and if you are dividing by niche count, so in that case you are also getting a solution. So when this solution will go for your selection operator, go to the selection operator and will compete for either tournament selection or or in other method basically. So this solution will also win the tournament because I have reduced the fitness of the other solution. So therefore you will also get the other local optimal solution. So population will be not only in at the global optimal solution, so this will also be distributed somewhere here. So you will also get the local optimal solution of the problem. Yeah. So he also asks whether it is a robust way. Okay. Now question is that this is actually the problem of this particular method, discount. So if you remember that sigma value you have to define. Now sigma is a user defined parameter. That means depending upon, so you may get all the your local optimal solution or you may not get because of the sigma value. And if you are using appropriate value of sigma, so in that case in that case you will get the local as well as global optimal solution. So I'm not telling whether this is a robust solution. Certainly if you are applying appropriate value of sigma, then certainly you will get. So therefore it is not very robust because sigma is again user defined parameter. So you have to define the parameter. So we'll also discuss there is another your algorithm, we call it NSGA. Okay. So NSGA, and basically I will discuss NSGA 2 when I will discuss multi-objective optimization problem. Okay, so multi-objective optimization problem, then I will discuss what is NSGA 2, and there actually, so the idea here, suppose the niche count I am calculating. So idea here is that I would like to avoid the crowded solution. That means I would like to reduce the fitness of the crowded solution because I would like to keep some solution which are basically away from the global optimal solution. Now this crowding criteria or crowding the crowded distance is implemented using niche count. So now NSGA 2 we have a different methodology that is more effective, okay, to basically implement the crowding criteria. So that will be discussed when I am discussing the multi-objective optimization problem, and specifically I will discuss about the NSGA 2 algorithm. Okay, so there are two algorithms, NSGA 1, NSGA and NSGA 2. So NSGA 2 is a very good algorithm for basically solving multi-objective optimization problems. So that will be discussed. Yes, so there is another question, the random mutation. What is the idea of selecting delta? Okay, which, so basically, so if you are using the delta value, so this is the maximum perturbation basically you are doing. So now I would suggest that you apply the simulated binary crossover and simulated binary mutation. So that is much better algorithm than this yeah, so this random mutation. So I think that you can use in case of ZA. Okay. Then so we have not discussed about so there is another algorithm, we call it evolutionary strategy. So there I will discuss about the random mutation. So far we have discussed genetic algorithm. So in case of genetic algorithm, so we are using both crossover and mutation. So we are using both crossover and mutation. But in case of evolutionary strategy, so we are only using your mutation, and that is basically random mutation. So there I will discuss you how actually only with the mutation itself you will be able to create, or you will be able to reach the global optimal solution of the problem. So that will be discussed in the next class. Okay, then so there is no live question as of now anyway. So if I am getting any questions, certainly I will try to answer those. But I would like to mention here. So in the next class, so or basically next in the coming weeks. So I have already discussed the R programming. So already one video has been posted. So you can go through that. You will get the basics of R. Okay, so how you can install R, and then how basically you can write a statement and logical statement. So that basically you please do that one. So once you're learning R, so you can use R for solving the optimization problem. So I will also post another video and another lecture in next week. So that will be the second lecture on R basic. So you can learn how to plot a function. It may be a single variable function, or it may be a multivariable function. Suppose you would like to plot a your surface. Okay, so that also you can plot using R, and you can actually you can plot contours. Okay, so that has been discussed in that particular video. So you please go through that video, and I will also give some more videos related to MATLAB now. So I have not discussed about how you can solve an optimization problem using MATLAB. So MATLAB is also a very powerful your software. So you can use the MATLAB toolbox, optimization toolbox, for solving a very complicated optimization problem. Okay, so I will give initial videos, so maybe 1 or 2 videos. So basics on MATLAB, so how you can write a statement in MATLAB, how you're writing an code, and how you're running that particular code. So that will be discussed initially, and after that I will show you how you can solve an optimization problem both using classical method as well as non-classical method using your MATLAB. So MATLAB toolbox has all the algorithms. Suppose the Newton's method you have discussed. So exactly Newton's method we are not using, but we are using quasi-Newton method. Okay, so that is there in MATLAB. So I also discuss in my class that basically the calculation of Hessian matrix is not easy basically. Okay, so if your problem, so therefore these algorithms, they don't use the Hessian matrix, actual Hessian matrix, but they approximate the Hessian matrix. So it's a quasi-Newton method. So that basically the MATLAB functions are using. So you can use those functions. There are several functions actually for solving classical function for solving classical algorithm function for solving optimization problem, and we'll also discuss how you can solve a genetic algorithm using MATLAB single objective optimization problem or multi-objective optimization problem using MATLAB. So that also will be your discuss. Okay, so I will post some or there will be a specific lecture on MATLAB, so that you can use. And apart from that, I also discuss how you can solve an optimization problem using Excel. I have solved the linear problem, but non-linear problem also you can solve using Excel solver, and that also I will discuss, or maybe there will be a specific video on solution of non-linear optimization problem using Excel solver. So if you have any question related to this, or if you want to know actually what will be there in this particular video, so you may ask. Okay, then as there is no more question, so I don't see any question are there. So yeah, there is no question. So then let us stop this particular session here. So thank you very much for attending this live session. So anyway, so this is the second live session. There will be another live session in the next your month. So there will be another one. So if you have any if you need any clarification there also you can ask, or if you have any question you please write to us. We'll try to respond that one. Okay, so thank you very much. So let's stop here.